In the previous part, we saw that carbon is the fundamental building block of life. Every living organism on Earth is built from it. We also saw that carbon enters the biosphere in a very specific way, through carbon dioxide in the atmosphere. Through photosynthesis, plants use sunlight to convert carbon dioxide into organic matter, forming the basis of all ecosystems. From there, this carbon moves through the entire biosphere. It flows from plants to animals, into soils, and back into the atmosphere in a continuous cycle. In this sense, nearly all life on Earth is built from carbon that was once in the air as carbon dioxide. But if carbon is so essential to life, a deeper question emerges: how does it move through the Earth system? And what determines the changes in its concentration over time? We often think of carbon dioxide as something that drives climate change. But what if, in part, it also responds to it? Ice core records from Antarctica provide a remarkable window into Earth's past. Trapped air bubbles preserve snapshots of the atmosphere going back hundreds of thousands of years. When we look at these records, a striking pattern emerges. Carbon dioxide and temperature move together. As temperatures rise, carbon dioxide levels increase. As temperatures fall, carbon dioxide levels decrease. This relationship appears again and again across glacial and interglacial cycles. It is one of the most robust observations in paleoclimate science. But when we look more closely, something interesting appears. In many cases, changes in temperature seem to precede changes in carbon dioxide. This does not break the connection between them, but it raises an important question. If carbon dioxide is only a forcing, why does it often follow temperature? The data suggests something more dynamic. Rather than a simple one-way cause, we may be looking at a system with feedbacks. A system where carbon dioxide both influences and responds to changes in climate. This raises questions about interpretation. If two variables move together, it does not immediately tell us which one is driving the system, or whether both are part of a deeper process. Correlation alone is not enough. To understand what is happening, we need to look at the mechanisms. How does carbon dioxide actually move through the Earth system? What controls its concentration in the atmosphere? To answer that, we need to shift perspective. From carbon dioxide as a static quantity to carbon dioxide as something that flows. One of the simplest and most important mechanisms comes from basic physics. Carbon dioxide dissolves in water. During this process, water and carbon dioxide form carbonic acid. The amount of carbon dioxide that water can hold depends on temperature. This relationship is described by Henry's law. Cold water can hold more dissolved gas, while warm water holds less. This is something we can observe directly. Just try opening a can or bottle of warm and cold carbonated drinks, or try pouring warm and cold beer into glasses. The same principle applies to the oceans. As ocean temperatures rise, the solubility of carbon dioxide decreases. Some of the dissolved carbon dioxide is released back into the atmosphere. When oceans cool, they can absorb more, so some of atmospheric carbon dioxide dissolves in water. This creates a natural link between temperature and atmospheric carbon dioxide. It does not require biology. It does not require complex feedbacks. It follows directly from physical chemistry. The temperature we have been using so far is not measured directly. It is derived from benthic oxygen isotope records, one of the most widely used proxies in paleoclimate research. These measurements are based on the ratio of oxygen isotopes, primarily oxygen-18 and oxygen-16, preserved in the calcium carbonate shells of microscopic marine organisms called foraminifera. As these organisms grow, the isotopic composition of their shells reflects the temperature of the surrounding seawater and the global distribution of ice. Colder conditions and larger ice sheets tend to increase the relative abundance of oxygen-18 in ocean water, leaving a distinct signature in the sediment record. But this oxygen isotope is not a simple thermometer. It reflects multiple aspects of the climate system at once. It is influenced by deep ocean temperature, by the volume of ice stored on land, and by large-scale changes in ocean circulation. These components are not independent. They evolve together as the climate system changes. This means that this proxy does not represent temperature alone. It records a combined signal, an integrated response of several interacting parts of the Earth system. When ice sheets grow, the signal changes. When oceans cool, it changes again. When circulation shifts, it responds as well. In this sense, the oxygen-18 isotope can be understood as more than a proxy for temperature. It is a reflection of the overall state of the climate system. If we take this combined signal and translate it into an effective temperature, we can use it to estimate how carbon dioxide should respond through temperature-dependent solubility. This is a simplified approach. It does not explicitly include ocean circulation, biological activity, or regional feedbacks. Instead, it applies a basic physical relationship, the dependence of gas solubility on temperature. At first glance, this might seem too simple. The climate system is complex. Carbon moves through multiple reservoirs, many processes operate at the same time. And yet, when this transformation is applied, something unexpected happens. When the estimated carbon dioxide curve is compared with ice core reconstructions, the similarity is striking. The timing aligns. The structure is reproduced. Major transitions appear in both records. This does not mean that temperature alone controls atmospheric carbon dioxide. Instead, it points to something more subtle. The input signal derived from oxygen-18 isotopes already contains multiple components of the climate system. It reflects temperature, ice volume, and large-scale dynamics acting together. At the same time, the match is not exact. The transformation is simple. The climate system is not. Processes such as ocean circulation, regional variability, and interactions within the carbon cycle all influence how carbon dioxide changes over time. However, it is well established that the oxygen-18 isotope signal is strongly influenced by both temperature and global ice volume. Since ice volume itself is closely linked to temperature, this suggests that large-scale climate changes are deeply interconnected. When we compare temperature reconstructions with atmospheric carbon dioxide records from ice cores, a consistent pattern emerges. Changes in carbon dioxide often follow temperature variations. At the same time, as we saw in Part 5, changes in vegetation can precede temperature shifts, and their energetic impact is not negligible. Taken together, these observations suggest that carbon dioxide variability is not driven by a single factor, but emerges from the interaction of multiple components of the climate system, including temperature, ice, oceans, and the biosphere. But this is only part of the system. Carbon does not move only through the ocean, it also moves through life. As we saw in Part 7, carbon dioxide plays a direct role in photosynthesis. Plants absorb carbon dioxide, store it in biomass, and release it again through respiration and decay. These processes are fundamentally different from ocean-atmosphere exchange. They are not governed by solubility alone. They depend on water, nutrients, light, and the structure of ecosystems. They respond differently. They operate on different timescales. And they modify the carbon cycle in ways that cannot be reduced to temperature alone. If we want to understand what shapes atmospheric carbon dioxide over longer timescales, we need to look beyond physical exchange. In the next part, we turn to this other side of the system. Not just how carbon moves, but how it is stored, locked away, and released again over time. In the next part, we will discuss the changes of carbon dioxide in the long term, while strictly remaining within the boundaries of widely accepted science. We will explore how it moves through life and what causes its fluctuations over time. If you liked this part, don't forget to share the video so others may also enjoy it. Also remember to like the video and subscribe to the channel so you don't miss the next part and other exciting videos released in the future.